Calculus. So, I'm going to be looking at, in these next two videos, the idea or concept of continuity. So, this first video is going to primarily focus on the definition of what it means to be continuous, a continuous function, and we'll get a little bit into then how do we determine continuity and prove that a function is continuous with some explicit examples in the second video. So first, what is continuity? So we kind of have this, I want to say, informal definition as of now of what is continuity. So the word continuous meaning, okay, there's no breaks or holes in the graph, but that doesn't necessarily really give us a whole picture of what's happening. So formally, continuity is defined by three key features. And these three things have to be met in order for us to have a quote-unquote continuous function. So first is that the function value exists. Okay. So A is, whoa, big. Let me fix that. So f of A exists. So continuity, let's be more definitive, at a point A. So first off, the function value exists at a particular point. So that's our first part to fulfilling continuity. Second part is that the limit as x approaches a of our function also exists. Our last part would be, this is what I would call like the linchpin, the closer for our definition of continuity, is that this limit value, whatever this comes out to be, is exactly the same function value. These three conditions have to be met in order for us to say that a function is continuous at a particular point. Now, visually, why do we need all three of these? Can't we just do it with one of these? So here would be an example. Let's say we're zooming in on a particular graph. So this would be an example of the limit existing. So I'm going to number these, kind of reference it a little bit. It's condition 1, condition. So this is an example where condition 2 has been met. The limit is going to be at x. So the limit as we approach A exists, but f of A does not exist because there's no actual function value at that point. There's an open hole there. Then we might have a situation like we saw in assignment number 1. Maybe we have something like this. So we meet condition 1. And again here, x equals A. So we meet condition 1, the function value exists, but condition 2 is not met because the limit doesn't exist. Now, well, what if we meet the first two conditions, but we don't meet the third? What does that look like? Then we would have something like this picture up here, but it looks something like this. So here, conditions 1 and 2 have been met, but condition 3 has not been met because we can see that the limit would give us a particular answer while the function value is a different answer. So again, this is happening at x equals A. So this is why we need all three parts to be in agreement in order for us to say that a function is continuous at that particular point. And again, a non-calculus, non-mathematical way of saying that a function is continuous is to say, well, if I were to draw the graph and never lift up my pencil as I draw the graph, then that would make a continuous function. All of these cannot be drawn without at some point you lifting your pencil and creating the hole in the graph like we see here, or this is not continuous, there's a jump. Here again, there's a jump. So anytime, this is where we would say the function is not continuous. There's a discontinuity there. Now, some of these are removable discontinuities, like this example here, because it's a hole in the graph. This would be an example of a non-removable discontinuity. There's no way for me to patch this up. I would literally have to take this chunk of the graph and like move it up here, and we're not going to do that. So this would be a non-removable discontinuity. So I'm going to label that non-removable discontinuity. And these are, so remember, we can remove them using our analytical skills and techniques that we learned last section. Removable continuity. So this is the definition. We need to, whenever we're asked to check if a function is continuous, which we're going to need to do as we encounter theorems later on in the course, and it's actually going to happen in the next section where we start talking about different theorems like intermediate value theorem, extreme value theorem, all of those theorems. In order for us to use them, we have to know if the function we are looking at is continuous. So we will have to prove that the function is continuous. I can't just say, yeah, this is continuous, I'm just assuming it. No, we have to prove by going through these steps that the function is in fact continuous. So in the next video, what I'm going to do is now start getting into actually proving some functions. So we're going to be given different functions, and we're going to go through this definition one piece at a time, and kind of like a little checklist to show, therefore, this function we know is continuous, and be able to point if it in fact has things like a removable discontinuity, a hole in the graph, an asymptote. We can then say, hey, it's continuous, except for here, this is where it's not continuous. So that'll then help us out later on in being a little bit more descriptive with the graph.